Hello, everyone. So far, we have covered basics of Python programming, object-oriented programming in Python, and also important libraries and packages such as NumPy, Matplotlib, and Pandas. And now we are at a very exciting point where we can talk about machine learning in Python using Scikit-learn. So we're going to start this lecture by briefly discussing the main concepts and ideas behind machine learning to motivate the use of machine learning in recent applications. And then after that, we're going to see how we can actually apply and develop machine learning methods using scikit-learn, which is a popular library in Python for machine learning algorithms. So the first question we want to answer is, why should we use machine learning? Let's say that you want to design a system for predicting bank loan default based on several features, such as income, debt, for different applicants, and you want to figure out the risk in terms of bank loan default to better make decisions for your financial company. So there are two main ways to solve this. So the typical, or classical programming approach is that you can start by writing down a step-by-step instructions or rules. And that's what we have in the figure on the left side. So this means that you have these features such as income and debt, and then you write down some rules. For example, if the debt to income ratio is greater than some number, so you have to do your research, figure out what those numbers are. Then we find some responses, meaning that yes, if, for example, the ratio of debt to income is greater than 0.5, then it is very likely that the applicant won't be able to pay the loan on time. But on the other hand, this is, very time consuming and labor intensive because you have to write down these rules. And then if there are changes in your problem, you also have to change these rules. The other way to solve this problem is using machine learning. So here, what we really want to do is to provide these features, meaning that in this case, income and debt, and also some responses, meaning that based on the observations that we have or historical data, we have information about people who previously were able to get loans and their information, including income and debt. And we know that, whether they paid their loan on time or not. So we do have some responses for these, group of people that already have been granted some loans. And therefore, in this case, the goal is that to use machine learning to actually provide us with these rules, right? So how can we distinguish between applicants that are able to pay off their loan and applicants who fail to do so? And here on the very right side, I have an example of this, right? So you can see that in this case, each data point, right, has these XY coordinates. One is debt, the other one is income. And you can see in this, synthetic data set that we obviously have a clear separation between these two classes. And the goal of machine learning is to find the rule that separates these two classes. So this means that now, if we find this rule and we have some new applicants, we will be able to figure out how to identify whether they're going to, or predict whether they're going to have problems with paying off their loan or not. So therefore, to recap what we just mentioned, when we have a machine learning system, this means that it is trained rather than being explicitly programmed, right? So that's kind of like, one way of thinking about machine learning systems. And therefore, the benefits are that, machine learning systems are in general easier to develop and maintain as long as you have enough data. And also, they can be more accurate than explicitly programming machines. But we do have challenges too, right? So as I just mentioned, we do need, features and responses. So in this case, features are income and debt, and responses are whether they, fail to pay off their loan or not, right? So that's what we call as label data. So label data means that you have features and corresponding responses. Another example of this, if I want to maybe clarify a little bit more, this like, data labeling. So let's say you want to develop a machine learning system to predict whether a medical image is normal or abnormal. So in this case, we need to hire some, physicians or some experts to look at some medical images that already we have and provide responses or labels for those images by telling us whether there's any kind of abnormality within each image or not, and that will be our labeled data set. And also we have other challenges too, because as machine learning methods become prevalent in high stakes applications and in safety critical applications, we have challenges to make sure that human users understand and trust these rules. For example, in the medical imaging case, we need to trust a machine learning system that predicts whether a medical image is normal or abnormal. And if the machine learning system makes wrong predictions, that can be really like catastrophic. So therefore, we always have to make sure that we understand and trust the rules that machine learning models they provide. And so just, to emphasize this in machine learning, data labeling, because that's a term that, you hear a lot, involves assigning informative labels to raw data like images, text files, or videos. And, machine learning in general, in terms of like differences between like a statistics, optimization, and machine learning, you can think about it in a way that machine learning really moves beyond the confines of these traditional domains. Because in machine learning, first of all, we want to be able to handle large and complex data sets. And what this means is that, we need a combination of both math and coding skills, right? Because in some cases, you need to be able to handle, millions of data points. So that's something usually we don't discuss or take into consideration when we talk about traditional statistical techniques. But in these cases, we need to make sure that we can import the data, read the data, manipulate the data, and then feed that to some machine learning pipeline to extract some knowledge and information. And obviously, this course mainly focuses on coding skills, but we do have other courses that are more focused on math skills. And at the end, you want to have a balance of these two very essential skills. Okay, so now let's talk a little bit more about learning rules that we just mentioned, right? So, as we said with the, bank loan default problem, we have some data points represented by their coordinates, right, in a two-dimensional space or R2. As you can see here, you have this X1, you have X2. In this case, we assume that X1 is, what shows the debt, and X2 shows the income, right? And obviously, these numbers here are synthetically generated, so you can assume that these numbers can be multiplied by, let's say $10,000 or $20,000 or something to be more reasonable. And so the goal here is to develop a machine learning system that can take the coordinates, these x1, x2 values of a new sample and predict the label or outcome for that, right? And in this case, we're going to very soon see that we can use, for example, logistic regression to solve this problem and find this classification rule, meaning that this like, dotted line that you can see here that separates these two classes. But something that we have to think about, and this is one of the main distinctions between machine learning today and machine learning 10, 20 years ago, is that in many cases, we may have a lot of features. So instead of just debt and income, we may have debt, income, gender, occupation, location information, etc. And therefore, in these cases, we have a very special type of data that we call high dimensional data, right? So this means that instead of just having a two-dimensional coordinate system, we may have thousands or millions of dimensions or features. And this is exactly why deep learning methods are becoming extremely popular, because they are very good at both finding rules and also at finding good data representations, meaning that if we have very, very high dimensional data sets, they're able to extract the key information from this high dimensional data and then learn rules that can, for example, separate classes in that reduce dimensional data. And also we have other, again, applications or considerations here too, such as like limited data availability, for example, for the medical image data analysis that we mentioned. Usually, it is, difficult to have large amounts of labeled data because data labeling costs a lot. Because of the need for domain experts and people who understand these medical images. And also, a lot of these machine learning applications are really high risk, high reward type of investments, meaning that they are costly, but if they work, they're going to be very, very helpful and high rewards. So that's something to keep in mind. So now let's go get a little bit deeper into the underlying foundations of machine learning methods and deep learning models. That's also something we're going to cover in this course. So in general, we can follow this framework that we have here. I mean, obviously there are minor differences between different methods, but the general rule is this, that we start with the features, and from now on, I probably just gonna call them inputs. So inputs and features, we use them interchangeably. And we send them through some layers or data transformation. So this means that you get your input data, you transform this. You can do this multiple times, so it's not just like one time. This is the main distinction between machine learning 10, 20 years ago and machine learning today, is that we may have multiple levels of data transformation. And what this does, it gives us at the end what we predict as the output for that very specific input that we provided to the system. And the nice thing is that in most cases, for this data that we provided, these inputs, we do have the labels or the actual true outputs or expected outputs. So this means that now, at this point, we can compare these two. And this is what we call it as a loss or cost function, which really measures the discrepancy or disagreement between what we predicted and what the underlying or true outputs are. And this allows us now to send this information to some optimizer that can update the way that we transform the data. So usually these data transformation layers that we have, they have some weights or coefficients, and this optimizer tells us how to update the way we do those transformations. So this is very much similar to the example of linear regression that we had before, where we get some inputs and then we find a way that sum, right? We had those coefficients that we use in previous lectures. And the key question here is that what those coefficients or weights should be to get outputs that are as close as possible to the true outputs. And the way that we measure that is using this loss or cost function. Okay, so let's talk about categorization of machine learning algorithms based on two criteria. So one is based on data supervision, which refers to the data labeling process. So supervised learning algorithms are trained on labeled data, which means that each input data is paired with a corresponding output or label, right? So for example, in the case of medical image data analysis, meaning that for each medical image that we have, this can be a CT scan or something like that, we do have a label that says, for example, if this is normal or abnormal. So this is what is called as label data, and supervised learning means that we are training them on labeled data. The other type of machine learning algorithms is unsupervised learning. And in this case, these algorithms are trained on unlabeled data. So this means that in this case, you may have some CT scan images. You do not know which ones are, are normal or abnormal. So nobody has labeled them. That's why we call them unlabeled data. But the goal is to automatically find some interesting patterns or structures in the data. For example, can we automatically group them into two clusters, where one cluster are the ones that are more likely to be normal and another cluster are the ones that are more likely to be abnormal. So in this case, we don't have any supervision, but we do want to learn these types of structures. And as you imagine, we have a third approach, which is semi-supervised learning, which is a combination of supervised and unsupervised learning, where the algorithm is trained on a mix of labeled and unlabeled data. So some of the data points come with the input-output pairs, and some of them are just inputs with no outputs. We also can categorize machine learning algorithms based on model complexity. So in this case, linear models are the ones that they assume a linear relationship between the input features and output, right? For example, linear regression. That's a very classical example of this. We also have nonlinear models that can capture more complex relationships between inputs and outputs. And something I want to emphasize here is that neural networks are not necessarily the only nonlinear models that are becoming very popular and very important, but there are also other ones too, such as like decision trees and so on. And therefore, this is just to keep in mind that we have a wide array of nonlinear models. But a subset of this is what is known as artificial neural networks, deep neural networks. In many cases, we just use these interchangeably, although there are technically differences. For example, when you say deep learning, it is supposed to be neural networks that they have many hidden layers, whereas just neural networks usually like have a few hidden layers. But these days, in many cases, we use them interchangeably. And these are a subset of nonlinear models. And the cool thing about them is that they learn hierarchical features, as we're going to see very soon in this course. However, in this course in general, we are focusing on supervised learning, meaning that in cases that we do have labeled data, each input data point is paired with the corresponding output. And this is the most common type of machine learning, and usually the sort of like the backbone of many other types of machine learning algorithms. So one way to think about supervised learning is that you always want to make predictions, right? So meaning that you want to predict some outputs, and depending on the type of output, these supervised learning methods are divided into regression and classification. In regression, we have quantitative labels. However, in classification, we have qualitative or categorical labels. To show the difference here, on the left side, you can see that this is a regression problem. Let's say you have years of experience as your X value or input, and here the output or the Y value is the salary, right? So you want to see if you have a new employee with a number of years of experience that you have, if you can predict the salary for that new employee, right? And in this case, we do have these data points that are already given to us, and we want to use this to develop a model to figure out, well, what is a reasonable salary for this new, new employee with the, like, let's say 20 years of experience. But in this case, we are trying to predict a quantitative label. On the other hand, on the right side, you can see that with the classification, right, you may have, again, like bank loan default, where the answer is yes or no, or like if you have an email filtering system where you want to label each email as a spam or not a spam, or a medical image analysis where you want to label each or predict labels for each image as being normal or abnormal. So in this case, we do have qualitative or categorical labels. And in future lectures, we're gonna first talk about regression, and then in the subsequent lecture, we're going to talk about classification. So let's very quickly talk about mathematical building blocks of machine learning. So in supervised learning, which is the main focus here, the goal is really to find a mapping or function from inputs, which we also call these features, or in statistics, we like to call them predictors, to some outputs. And remember, these outputs are the ones that we just mentioned that either they can be quantitative or qualitative. And in general, we assume that we have a data set with n input-output pairs, and we use this small n to index these data points, right? And this n goes from 1 to uppercase n. So the uppercase n is the total number of samples that we have. And then we also assume that each of these inputs xn is a d-dimensional vector or array, meaning that we have d features. In the case that we have, let's say, only income and debt information, that means that d is equal to. But as we said, in many interesting machine learning applications, we have high dimensional problems. So this d can be thousands or millions, in the order of thousands or millions. And then in the case that we have a classification problem, these YNs are categorical, and therefore in the multi-class classification with C classes, we can give them these labels 1, 2 through C. Although I have to say that these labels, when you do classification, do not have any numerical value anymore, meaning that in that case, just the difference between 1 and 2 is that all the data points with label 1 belong to the same class, and all the data points with label 2 belong to another class. But obviously, this doesn't mean that one class is 2 times the other one. So we do not really assign any numerical value to these. It's just more to distinguish between them. And if you have a binary classification problem, which means that we only have 2 classes, the situations where we have yes and no problems, then the labels are either 0 or 1, or sometimes we also may label them as -1 and 1. And as we just mentioned, there is really no numerical interpretation of these numbers, and as long as we just use 2 distinct values to represent these 2 classes, then everything should be fine. Okay, so now let's talk a little bit about model fitting, or also known as model training, right? Because we said that these machine learning algorithms are trained on data. So the first thing that we need to do for model training is to form something known as empirical risk, which is simply the average loss on the training data. So what this means is that we need to have a loss function, which we show that using this L. This function accepts 2 inputs, the true or expected output and the predicted output. And remember, the predicted output is the function of the input. And this theta here shows all the parameters that we have in our model that we need to find them. So that's why we use this semicolon here. So just to explain this, let's go back to the framework that we have here. So here we have the x, which is the input. This gives us f of x, which is the predicted output. We compare this with the true output, which is y, and this loss function, or L, measures the difference between the two. And all these weights or parameters that we have here, these are known as theta. So in this case, we have our input, thetas, and also the true outputs. And since we're using this small n here for indexing, we take this from 1 to uppercase n, and this is what is known as the empirical risk. So let's talk a little bit about this loss function that we have here. If you have a binary classification problem, we can use a loss function, which is an indicator function. So when you have an indicator function, this I function, if this condition is true, then we get 1, meaning that if y is not equal to y hat, and otherwise we get 0. So what this does, if we plug this back into what we have here, is that if the true output and the predicted output are not equal, right? In this case, we get 1. So this means that we have 1 misclassification. And this summation overall gives us the total number of misclassified data points. And divided by the total number of data points, that gives us misclassification rate. And obviously, when you have a machine learning system, you want to reduce or minimize the misclassification rate. And you do that by finding the best choice for this parameter theta. Therefore, putting back everything together, this is what is known as empirical risk minimization, or ERM, which means that you want to find parameters theta that they minimize the empirical risk, right? So this is what we just talked about as the empirical risk. And now we want to find the argmin with respect to theta. And as we're going to see right now, there's a big difference between argmin and min, because when we are using argmin, what we are saying is that we don't want to necessarily find the minimum value of this function, but we want to know what value of theta leads to the minimum value of this function. This is very similar to when you working with NumPy arrays, we use min and argmin, right? Remember, min of a 1D NumPy array is the minimum value that you have, but argmin gives you the index where that minimum value resides, right? So that's kind of like the difference. And we can do the same thing here, and you can see how we can use different libraries. So we use import numpy as np. We are gonna use matplotlib. We know about customizing figures. So here we are customizing the font size and figure size. And then we're using np.linspace to create 1,000 data points from -3 to 2. And then we're going to generate the outputs which are related to the inputs via this equation, x squared plus 2x plus 3. And then we plot these xy values to see how this looks like. We're going to use the np.argmin to find the index for the minimum value. And using this, now we can plot actually where the minimum value is. And also, we're going to use plt.annotate to actually, annotate our label and show exactly where the minimum value is. So if I run this cell, you can see that as we expect, this is our function that we have. The minimum value is 2, the minimum value of this blue function, but the argmin is -1 because the value of -1 leads to the minimum value, which is 2. So that's something you always have to keep in mind when you're working with machine learning models. We really want to find the argmin with respect to the model parameters to know what model parameters give us the lowest disagreement between true and predicted outputs. Okay, so we just talked about a loss function for classification problems where we have categorical labels. But as you imagine, that approach does not really apply to regression problems where the output is quantitative and it can be any real valued number in general. Therefore, the main reason that we have to study classification and regression tasks separately is that the loss function for these two different types of tasks are usually very different. And therefore, let's look at one example of loss function for classification problems, which is the quadratic loss function. So what this loss function does is subtracts the true output from the predicted output, and then we find the residual and raise this to the power of 2. Obviously, in this case, it doesn't matter if we use y hat minus y or y minus y hat, but the idea is that we have to find the difference between true and predicted output and find this residual and raise it to the power of 2 to make sure that it's also not negative. Because in that case, if this becomes negative, when you add these disagreements or these values of loss functions, they can cancel each other, and that's not a really good idea. So therefore, in general, as you can see, one of the properties of loss functions is that they should be non-negative. And therefore, based on this, if we plug in this back to the empirical risk that we had, you find this 1 over n, sum over n of these residuals raised to the power of 2. So this fx and theta is now, in the place of y hat. And this is what is known as mean squared error, or MSE, which is a very well-known function. And the underlying assumption for linear regression, it's simple, is that when we have some inputs with the features, so these x1, x2 to xd are the features, we can find a weighted sum, or also known as a linear combination. And here we can also simplify these by writing these as dot product of two vectors w and x, because if we have two vectors and find the dot product, as we have done before, that's equivalent to the sum of the element-wise products, which gives us this dot product or inner product. And therefore, in this case, all the values that we have for this W1 to WD, and also this W0, which acts as the bias or the y-intercept, they are considered to be the weights of the parameters of the model that we have, right? So this theta that you see here are all these unknown parameters that we have, these W0, W1, WD, and the goal is to find the best values for these such that we minimize the value of these mean squared error. Something that is important in machine learning is that what we really care about is the generalization of machine learning problems. And just to show the difference, so when we do training, we can develop machine learning models that they can literally memorize the data that they have seen. But what we really care about is that how well this machine learning model that we have trained generalizes to new or unseen data points. And this is the main idea behind generalization. And one of the main challenges that we have is that the model can become overly sensitive or specialized to the training data during the model fitting or training process. And therefore, it may not perform comparably when applied to new data points. And therefore, for this reason, we always want to make sure that we can evaluate the generalization performance of machine learning models, which means that at the minimum, you have to always have two data sets, one for training and one for testing. And this is the idea behind train test split. So in this case, as the name suggests, we are going to divide the data into two parts, a training set and a test set. And then the training set is used to train the machine learning model, which means that we find those unknown coefficients or weights, like for example, the W0 through WD that we just saw. And the test set is used to evaluate the performance on new or unseen data, which is a holdout data set. And in this case, you can find the training risk, which is the sum of the loss functions evaluated for the data points that belong to the training data. And then we can find the test risk, which is the sum of the loss functions evaluated at the test data points. And these two values should be comparable. Overfitting happens when the test risk is much greater than the training risk, which is not desirable. So overall, once you find this L train and L test, you want to make sure that they're comparable. And if for some reason the L test is much greater than L train, then we know that we have a model that is overfitting and not generalizing well to new or unseen data points. So here we can show this or illustrate this. So you get your original label data, and you divide this into training and test set. One caveat here is that if you do this train test split and use the test set multiple times, you may actually end up overfitting to the test set itself. So a good practice is to just use this test set only one time. But that really depends on the application, because in many cases, you may only have one training and one test set. But that's something that we will talk about that more later. But for now, the main thing that we have to consider is that once we have a given data set, we need to at least create two data sets from that, training and testing sets, to be used, one for training and the other one for evaluation purposes. So at this point, let's put everything together by creating a synthetic data set for a regression problem. And we're considering a 1D regression problem, meaning that we only have one input X and we have one output Y. So this is what is, matches very well with what we know from linear regression, which is Y equals mx plus b, where m is the slope and b is the y-intercept. And even to make this simpler, we are going to assume that we do not have an intercept, and the goal is just find the slope. So when we create the data in this case, we are going to make sure that we just use y equals mx. There is no b here, and we just want to find the slope. During the case that we want to, the step that we want to, generate this data, we also add some Gaussian noise. This is just to make this more resembling real-world data sets, because in general, in real-world problems, we always have some measurement noise or observation noise. So as we're going to see, when we create our data set using this equation, we're going to add also some Gaussian noise. And then we're going to split the data into training and testing sets. And one way we can find this slope m here using the derivative approach, meaning that once we find the loss function, we can actually find the derivative with respect to m and set that equal to 0, because here we only have one unknown during the training part, which is this m. And this is doable in this case. But in general, if you have multiple of these, unknowns, we cannot easily use the derivative approach. And for that, we can use the Scikit-learn's method or linear regression class, which can help us to solve this linear regression problem. So in this case, we want to one time solve this problem from scratch by using the derivative approach. And then we're going to utilize linear models, linear regression from Scikit-learn. And just to put this into context, we know that, in this case, Scikit-learn is the library or package. Linear underscore model is the module, and linear regression is the class that is included inside this module, right? So this connects us with, I believe, lecture 9, where we talk about modules and packages. So now we understand the hierarchy here using this dot notation. And then once we find the slope, now we can predict the output or y values for the testing set. Okay, so let's start with the step 1, which is generating a synthetic data set. In this case, we're gonna import numpy as np, import matplotlib.pyplot as plt. It's always a good idea to set the random seed for reproducibility, so you don't have to do this, but if you use this line, you'll see that you get consistent results. Then we're going to generate our synthetic data set. And I want to be clear, the reason that we are generating synthetic data set here is because we don't want to use a real-world data set. In practice, we usually have a CSV file, we have a data set that we import, and we don't really know the true underlying equation that generated the data. But in this case, we want to really simplify the process. So we use this known equation to generate the data. And the goal is that, well, can we now estimate this m true or not, or the truest slope? And in order to do this, we're going to use the NumPy's random a module, and inside that we're going to use rand, which gives us 100 data points in 1D. And then we're going to set the m true to be 5. And we're going to generate these outputs by simply multiplying m true by x, right? So this is that linear relationship with no intercept. To make this a little bit more interesting, we're going to add some normal or Gaussian noise. There we have this SKL, which is the standard deviation for this normal distribution. And after that, we can use plt.scatter to have to visualize the relationship between x and y. So that's what we talk about when we had matplotlib. The plt.scatter is great for visualizing relationships. And obviously, we use the x label and y label to make the figure more readable. So here you can see that this is the data that we created, right? So this follows a linear trend, but also we added this Gaussian noise to make sure that this is not trivial, because if you don't add that, you can literally pick 2 data points and draw a line that goes through them, and that's the solution. So it becomes almost a trivial problem. Just to make sure that this problem has the right shape or size, you can see that we can look at x and y values, and they both have 100 elements, right? So this means that each input is paired with a corresponding output, right? So if you have this 2D coordinate system, that we have an x value and we have a y value. The next thing that we have to do is to split the data into training and testing sets. In order to do that, we can use Scikit-learn. And inside that, we have a model selection module. And inside that, we can use train test split. And the way that this works is that for train test split, which is a built-in method in Scikit-learn, you can pass in the x, y values and the desired test size that you want. So 0.2 means that you want to have 20% of your data for testing and 80% for training. Also, because this involves generating a random number to separate the 2 classes randomly or the 2 data sets. So we can use this thing called random state. So again, you don't have to specify this, but if you set this equal to any number that you want, you will get consistent results if you run this cell multiple times. And so if you use 0 here and use np.random seed that I used before, you should be able to get exactly the same results, even though these are random numbers, they are generated in the same way. So that's the idea behind random state. So if you run this cell, you will see that now X-train, the training data, we have 80 samples. And this makes sense because 80% of data should be for training, and we have 100 data points. And then for testing, we have 20 data points. And then their corresponding labels or outputs, like 80 for training and 20 for testing. So let's say now we use 2 scatter plots to individually look at training and testing data points. And I'm going to use different colors. So blue for training, red for testing. We also give them labels. And we're also using plt.legend. So you can see that why knowing matplotlib is essential for machine learning and data science, because we can use them a lot for visualization purposes. So you can see that here we have the training data points, we have the testing data points. Everything looks fine here. We do not have any of abnormalities. You can see that the blue and red dots here are distributed almost uniformly, which is great. And remember that in many cases, you're already provided with this training and testing data set. So you usually do not want to generate your own data. But again, this is just for illustrative purposes. So now let's look at how we can find the slope using the derivative approach. So in this case, you have to form that empirical risk by having this average of loss function. And in this case, the predicted value is simply m times the input, and true output is yn. And now we can take the derivative of this with respect to the slope, which is m. So if one way to do this is to call what we have here as, let's say, z or something like that, to be able to use easily the chain rule. And then we can take the derivative of this with respect to m. So then we get derivative of z squared, which is 2 times z. And then we have to take the derivative of this z with respect to m, which is xn. And once you find this derivative, we set this equal to 0 and solve for m, which gives us this somewhat familiar equation because we have used this before, which is the sum of the products of xn and yn. So each xn and each yn is one data point that we have, one input-output pair. And then in the denominator, we have the sum of the squares of inputs. So in this case, we can just write exactly what we have here to implement this. So we can multiply x train and y train, use np.sum to sum that. And in the denominator, we have np.sum x train raised to the power of 2. And then we can run this cell, and you can see that it tells us that the estimated slope is 5.18. Which this is a good result, right? Because we know that since we generated the data, the true value should be 5. So this is, reasonably close to that value. But let's see how we can use scikit-learn, like especially if we have a more complex problem and we want to solve this, how can we use scikit-learn's linear regression? So remember that this scikit-learn.linear model is a module in scikit-learn for using linear models. And inside this, we have a bunch of linear machine learning algorithms, such as linear regression, logistic regression, etc. In this case, we can import linear regression from this module. And the way that this works is that, remember, this is a class. So you have to first create an object. And in order to do this, you have to instantiate this. And once you want to instantiate these, there are some options. In this case, we know that we don't want to have the intercept term, so we can set that to be false, meaning that we just want to find the slope. So this is the object. This object does have a method called fit, which accepts the training data, x train and y train. And once you do the training, one attribute of this is this .coef or coefficient, which gives us the coefficient or that slope term m. And that's why I call it as m sklearn. So this is the m value that is estimated using scikit-learn, and the other one was m that we estimated using the equation that we derived ourselves. So let's see what we get here. And you can see that we again get 5.18, which is very close to what we had before. So this is great. This means that now, even if we have a more complex problem, we do not have to use, this analytical approach that we did here. We can just simply instantiate this object, use .fit, and then use .coef to find the coefficient. And if you want, we can even, although we know that these slopes are very close, we can even visualize this, right, by making predictions. So what this means is that when we have X test, we know that in order to predict the output for that, we just simply have to multiply the estimated slope by the input. So that's the m times x. And we do that one time for the one that we use the derivative approach. And we can also do this one time with this scikit-learn approach. And if you run this cell, you can see that this is the prediction model that we have. And the red dots here are the test data points. And you can see that both cases, they are identical, the derivative approach and the scikit-learn linear regression approach. This is the best we can do in this case with the linear model, because obviously if we have a nonlinear model, we might have been to better, approximate or go through these, red dots that we have. But since this is a linear model, the only thing that can really do is to go through, kind of like the middle of the data that we have. So this is a reasonable model for a linear regression problem. And we do have these issues with these scattered data points not being directly on this line because of that Gaussian noise that we added. So we can reduce the amount of noise to get closer, or we can increase it to make it even more difficult to solve. So all in all, the goal here is to show you how to use scikit-learn. So in many cases, you may know the model assumptions, but you don't know exactly how to do model fitting. But this is no problem because you can use scikit-learn. And the steps that you have to take are as follows. First, you choose a model. So obviously, as we go through these lectures from now on, you can see that we have multiple ways of solving problems depending on whether you have a regression or classification problem. For example, for regression, you can use linear regression. For classification, you're going to use logistic regression, and we're going to talk about this later on. We have not discussed this yet. Then you have to import the model. For example, for linear regression, we said from sklearn the linear model, import linear regression. Then you have to prepare the data, and this usually means that you need to find the features or inputs or independent variables, and then the target or the dependent variable, what you're trying to predict. And remember that the features, the one that are inputs, they're supposed to be 2D arrays. And the targets are usually a 1D array. So that's kind of like the distinction here. And then for the features that are 2D arrays, each row corresponds to one data point, and each column corresponds to one feature, right? So that's something that we have been using so far as the main assumption that we make, that features are usually in a 2D array where each row is one data point, each column is a feature. And the targets are usually 1D arrays because we are here trying to predict a single quantity or target, and it can be quantitative or qualitative, but anyways, it's one element that we want to predict for each input. Step 4 is to split the data so that we can measure the generalization performance, and for that we can use scikit-learn's model selection, and then we use train test split. Remember, this model is a class, so you have to now instantiate this and create an object. This object is equipped with a method called .fit, where you have to provide your training data. And finally, once you train your model, you can use .predict method and provide these testing data points to get predictions. So in the object-oriented programming lecture, we actually had a homework problem where you had to develop your own linear regression model, and you did exactly the same thing. You calculated coefficients, and then you made predictions. So you can see in that case, you had a very like simplified version of this to show you how this works in terms of like the big picture. And finally, you have to evaluate your model. So we're going to talk about this in the next lecture more, but there are different ways of evaluating models. If it's a regression problem, such as mean squared error, mean absolute error, or if it's classification, you have like things such as accuracy, precision, recall, and all of these are inside this module, which is called sklearn.metrics. So that really helps us to understand how scikit-learn works, right? So we have these different modules like linear model, model selection, metrics, which, these modules provide different functionality. And then for the homework for this problem, the main one is, in one case, you want to manually implement the train test split. And in this case, you can use all the NumPy's functionalities, but do not use exactly the train test split, which is included in scikit-learn, because that's our goal, to replicate its functionality. So this function should be called custom train test split. You assume that you are given a set of input features, and that's a 2D array, as we said, a 2D NumPy array. You have the corresponding outputs, which is a 1D NumPy array, and then the test size, right? And in this case, you can see that what you can do is to randomly shuffle your data or permute your data. And then based on that, you can split your data into a training and testing sets. And then you can return the values for X train, X test, Y train, and Y test. And as I said, the main thing here is that do not use Scikit-learn's train test split. And here we have one example that we have X, which has 4 rows and 2 columns, and Y is the array with 4 elements. And so we want to here divide these data into training and testing such that the testing set size should be 25%. And then in the third problem here, you again create a one-dimensional synthetic data set like the one that we did. And you apply the linear regression model from scikit-learn to this data set. This means that you have to do model fitting, you have to print the slope. And also in this case, you can see that we have this intercept term or y-intercept b. So that's kind of like the main difference. But other than that, you can see that we will follow the same procedures to instantiate linear regression and do model fitting and model training. And then also we have a variant of this where instead of linear regression, you're going to use ridge regression. And again, the goal here is to show you once you understand the basics of how scikit-learn works, we can use different implemented algorithms or built-in algorithms because they'll very much follow the same procedure. You just need to know how to instantiate them, and then you have to do model fitting and model training. Therefore, in this problem, we just want to show you how, you can use the knowledge that you have and extend this to solve another problem where you are here using this ridge regression. So here you have the documentation, some information that provided here that you have to provide this information about an alpha parameter. But this gives you a really good idea of, how you can apply your knowledge to use, other existing machine learning algorithms in scikit-learn.